Good morning, students. Now we will be discussing about electric dipole. So in this electric dipole, we will be discussing about what is dipole and its units and how to find the electric dipole moment. So we will be discussing about dipole moment and we will be finding the electric field on the axis of dipole and we will be finding the electric field on the perpendicular bisector of dipole, and after that at a general point of the dipole, and after that torque acting on dipole and we will be discussing about unstable and stable equilibrium, and finally problems on torque. Clear? So these are the summary of the entire lecture today. First, what is dipole? If two equal and opposite charges are separated by some small distance, say 2L, and the entire arrangement is called as electric dipole. Dipole means two poles, two polarities. So if two equal and opposite charges are separated by a distance 2L, means very small distance, then the entire setup is called as electric dipole, and we will measure the dipole moment for this electric dipole, and that dipole moment is having a magnitude of product of either of the magnitude of two charge and length between the two charges. So if you take 2ql, then this will give the magnitude of the dipole moment, and it is having a direction from negative to positive. It will have the direction from negative charge to positive charge. So what is dipole? Dipole is nothing but the two equal and opposite charges are separated by a small distance. Then that combination that setup is called as dipole moment, and that setup is called as dipole. And a dipole has some dipole moment which is equals to the product of the length of the dipole and the magnitude of the either of the two charges. We can take any one of the magnitude of the two charges. So, and the dipole moment has direction from negative charge to positive charge. This is regarding dipole moment. So dipole moment P bar equals to product of length of the dipole and either of the magnitude of two charges, and has a direction from negative charge to positive charge, and dipole moment is a vector quantity. It is having both magnitude and direction. So its units are charge. For charge it is coulomb meter. So dipole moment units are coulomb meter, not centimeter, coulomb meter. Now let us find the dipole moment for the given combination of charges. Here plus q minus q, coordinates are 0 comma a, and here also plus q, coordinates are a comma 0, and here minus 2q, coordinates are 0 comma 0. For this entire setup we are going to find the dipole moment. So here initially this is 2q, this 2q can be split into minus q and minus q, right? So we can split it up. So I am splitting it, plus q minus q, and at the same point another minus q is there, which will give the electric field, sorry, dipole moment. So from here to here, what is the dipole moment? P1, say P1, and here to here the dipole moment is P2. So and the distance will be a, and this distance will be a. So P1 equals to magnitude into length of the charge, P2 equals to magnitude times distance between the two charges. We know that dipole moment is a vector quantity, right? This is P2 and this is P1. So the resultant will be, these are mutually perpendicular, so the resultant will be making an angle 45 degrees with the either of the two dipole moments. So net P net. So the entire dipole moment means the net dipole moment will be P1 square plus P2 square. We can write 2 P1 P2 cos theta also, but since the angle between the two vectors, two dipole moments is 90 degrees, so that cos term will get eliminated. So we can write this only. So P square plus P square, which is equals to root 2 times P. So which is equals to Q times A root 2. Q times A root 2. This is the net dipole moment of the given set of charges. Clear? So the net dipole moment will be like this. This is P net, or here it will be P2. Here it will be. Here we can split the charges as minus q and minus q, and the distance between these two charges is a, and distance between these two charges will be a. Clear? This is the net dipole moment for the given set of combination. Like that, they can ask anything, any set of points. Now let us find the electric field. Let us find the electric field due to a dipole on the axis of the dipole. On the axis of the dipole. Electric field due to a dipole on axis of dipole. For that, what we have to do? First of all, take a dipole minus q charge, as q charge, and center is this one. So this will be L and this will be L. So we are going to find the electric field at a point P, which is at a distance of x from the center of the dipole. From the center of the dipole, the distance between the point and the center of the dipole, let it be x. So because of this plus q, the electric field will be in this direction, E plus q. Because of this minus q, the electric field will be towards the charge. So E minus q, and the net resultant will be E plus Q minus E minus Q, where E plus Q is greater than E minus Q. Why? Because L minus A is less than L minus X. L minus X is less than L minus A. So 1 by L minus X whole square is greater than 1 by L plus X. Clear? Now let us write the electric field. Because of plus Q, E plus Q will be K. What is the charge? Q. What is the distance? This is X, this is L. So it will be X minus L whole square. So X minus L whole square, and because of minus Q, the net electric field at that point will be K Q upon X plus L whole square. X plus L whole square. Now the net electric field will be, here whatever the denominator we have, the distance of the point from the center of the dipole, or from the either of the charges, we know that if distance is less, the electric field will be more. So that is why bigger one minus smaller one. So this plus Q, electric field due to positive charge is more compared to electric field due to negative charge. So E plus Q minus E minus Q. KQ constant 1 by X minus L whole square plus minus 1 by X plus L whole square. If we solve that one, KQ divided by A square minus L square, which is equals to A plus B whole square minus A minus B whole square. 4AB KQ 4X into L divided by X square minus L square whole square. This is nothing but net electric field at the point P. So we can modify it further. If the distance between the 2 points is very much greater than the half of the length of the dipole, then X square minus L square whole square will be X power 4. We can neglect L, because if this is 100 and if this is 0.1, so X square is 10 square, 10 power 4, 10,000 minus 0.01, very neglectable. So X power 4. So the net electric field will become K. This I am splitting into two parts. 2Q L, 2QL into 2X. 2 2s are 4, QL into X divided by X power 4. X cancels. So K 2, this is nothing but P bar divided by X cube. So which is equals to 2kP upon X cube. So that is the net electric field at a point P on the axis of the given dipole. Clear? So let us understand it once more. What we have done, we have taken a dipole and we are going to find the electric field at this point P, which is at a distance of x from the center of the dipole. Clear? Now what is the distance of point P from the positive charge from here to here, x minus L, and from here to here, what is the distance? X plus L. So now, because of positive charge, what will be the electric field at point P? It will be away from the point P and has a magnitude of kq upon x minus L whole square. Clear? And because of minus q, what is the electric field at that point P? The electric field will be towards the negative charge, towards the minus q, and has a magnitude of kq upon x plus L whole square. And if denominator has the more value, the resultant will have the less value. If the denominator has the low value, then the resultant will be more value. So when we are finding the net electric field at point P, it will be E plus Q minus E minus Q. Otherwise, by understanding here only, we can say that this is positive charge and is near to the point P. So this will have more magnitude compared to this one. So net electric field will be E plus Q minus E minus Q. E plus Q minus E minus Q. If you solve this one, we will get this value. If the distance of the point from the center of the dipole is far greater than the length of the half of the length of the dipole, then what will happen? This x square minus whole square, x square minus L square whole square will become x power 4. If we get cancel, we will get electric field on the axial line. So let us write it as EA. Why? Because on the axial line it will be 2 kp by x cube. Clear? Okay. Now let us calculate the electric field due to a dipole. Electric field due to a dipole on the perpendicular bisector of dipole, on the perpendicular bisector of the dipole. Further, what we will do, we will take a, and one more thing, there when we have done the on the axial line, net electric field will be away from the point P and minus Q plus Q, and the dipole moment is also minus Q2 plus Q, means same direction. Here the EA and P bar are parallel, not parallel, are in same direction, Here electric field on the axial line and the dipole moment both are in same direction. Now let us find the electric field due to a dipole on the perpendicular bisector of the dipole. Minus Q plus Q, center of the dipole, distance will be L and L, and we are going to find the electric field on the perpendicular bisector. On the perpendicular bisector of the dipole. It is at a distance x from the center of the dipole, and because of this, at a point P, because of minus q, the electric field will be towards charge, and because of this positive charge, the electric field will be away from the positive charge, means away from the point which are at a distance of r and r. This is theta. This is also theta. And now here if you observe, the electric field is in this direction and it will be in this direction. Now what is the angle between the two vectors? It will be 120 degrees. It will be 120 degrees. So the net resultant will be like this. So let us calculate that value. Or we can say that if you split it into components, then this will be theta. So this will be E plus minus q cos theta, and this is theta, 99 is theta, E plus q sin theta. Here also E plus minus q sin theta will get cancels out and we will get E plus q cos theta. Clear? Now electric field due to plus q will be at a distance of r. So k q upon r square, where r equals to this hypotenuse. So since it is a right angle triangle, side square plus side square equal to hypotenuse square. K q upon x square plus l square. R equals to root over x square plus l square. Now because of minus q charge, k q upon r square, k q upon x square plus l square. Now here, since the vertical components will get cancelled out, the horizontal component will get added and will give the net electric field, because of the dipole at a point P on the perpendicular bisector of the dipole. So net electric field will be E plus q cos theta plus E minus q cos theta. So 2E, I am considering this as E. 2E cos theta. Now what is the value of E and what is the value of cos theta? From this diagram, cos theta equals to what? Adjacent side by hypotenuse. So L upon root over x square plus L square. So 2 times k q upon x square plus L square times cos theta is L upon root over x square plus L square. Now E perpendicular equals to 2q into L into k divided by x square plus L square whole power 3 upon 2. So kp divided by x square plus L square whole power 3 by 2. Now as usual, if the distance of the point from the center of dipole is very much greater than compared to half of the length of the dipole, means x is very much greater than L, then x square plus L square whole power 3 by 2 will become x cube. X square or let us split it. X square whole power 3 by 2 is equals to x cube. So finally E perpendicular will become kp upon x cube, and we have EA equals to 2kp upon x cube. So the electric field due to a dipole on the perpendicular bisector of the dipole is equals to kp by x cube, and on the axial line of the dipole it will be 2kp by x cube. Now let us check out the relation between E perpendicular and E axial. So let us do it one more time. Here we have taken a dipole where the length of the dipole is 2L, and we are going to find the electric field on the perpendicular bisector of the dipole. So for that, the perpendicular bisector I have drawn, and the point is at a distance of x from the center of the dipole on its perpendicular bisector, and because of minus q the electric field will be towards the negative charge. Because of plus q the electric field will be away from the point P, away from the point P and point charge also. So here if you split it, if you resolve the components of electric field onto x and y axis, then the y axis components E plus q sin theta and E minus q sin theta will get cancelled. Here the important thing is that the point is at the same distance from the two both ends of the dipole, so the electric field will be same only. And since it is looks like an equilateral triangle, and it is an equilateral triangle, the theta also will be same for both charges, and the E plus q cos theta and A minus q cos theta will contribute for the net electric field on the perpendicular bisector. So that is why we are going to add the two, and we have solved the things. Clear? Now relation between E perpendicular and E axial. E perpendicular and E axial of the dipole. So we know that EA equals to 2kp upon x cube, E perpendicular equals to kp upon x cube. So E axial equals to 2 times of E perpendicular. Means for a given dipole and at a point x, if you find the electric field on the axial line, if you multiply it with 2, if you find the electric field on the axial line and if you divide it with 2, then you will get the electric field on the perpendicular bisector of the dipole. Sometimes they will give you directly the perpendicular bisector electric field, and we can convert it into electric field on the axial line by multiplying it with 2. Now perpendicular bisector completed and axial also completed. If they have given angle theta, or the point is making an angle theta at a from the center of the dipole, so at a general point, so I am considering a dipole plus q, and from the center of the dipole, from the center of the dipole at a point P, at a point P, we are going to find the, which makes an angle theta with the center of the dipole, we are going to find the electric field at this point. So I am going to find the electric field at this point, which is making an angle theta from the at the center of the dipole. We are going to find the electric field at a point P. And now here if you see, the dipole moment is in this direction, or we can say the dipole moment is this one. And if you resolve it into two components, you will get P cos theta onto the axial line of the point P, and you will get P sin theta also, which will act as a perpendicular bisector of the given dipole. So if you find the electric field at a point, if you want to find the electric field at a point P, if you resolve it in the dipole moment vector into two components, the component P cos theta will give you the axial line, will be along the axial line, and P sin theta will be exactly on the perpendicular bisector of the dipole. And now let us calculate the electric field at point P, which makes an angle theta with the center of the dipole. So at an axial point P, which is at a distance of x, we will get the electric field will be 2kP, but here P will be P cos theta upon x cube, and E perpendicular will be K, usually Kp by x cube, but here P will be P sin theta. So here if you observe, this is E axial, and this one we can write as E perpendicular. Since these two are perpendicular to each other, electric field will be net electric field. So net electric field equals, since they are perpendicular, E A square plus E perpendicular square. It will be, since Kp by x cube both are constants, Kp by x cube whole square, I am taking it out, so it will be 4 cos square theta plus sin square theta. Kp by x cube we can take the common from the root, then 4 cos square theta we can write as 3 cos square theta plus cos square theta plus sin square theta. Now here Kp upon x cube, sin square theta plus cos square theta is 1, so 1 plus 3 cos square theta under root of. So the electric field at a point P, the net electric field at a point P will be Kp upon x cube root over 1 plus 3 cos square theta. That is the net electric field at a point P, which makes an angle theta with the axis of the dipole. Here axis of the dipole, so En equals to Kp upon x. If it is on axial line, then theta will be 0, implies Ea equals to Kp by x cube root over 1 plus 3 2 Kp upon x cube. If theta equals to 90 degrees, which means on the perpendicular bisector, Kp upon x cube root over 1 plus 0, which is equals to kp upon x cube. Clear? So at a general point or at any given point, the net electric field will be En equals to kp by x cube root over 1 plus 3 cos square theta. Clear? So let us summarize the E perpendicular and E parallel. E axial, E perpendicular. So E axial equals to 2 kp upon x cube. E perpendicular equals to kp upon x cube. E bar and P bar are in same direction. E bar and P bar are in opposite direction. And EA equals to 2 times of E perpendicular. E perpendicular equals to EA upon 2. So these are the things where we can understand the A axial and E perpendicular. Clear? Okay. Now, what will happen to the dipole? If we place the dipole in an electric field? So before jumping to that, let us summarize that whenever a point charge Q0 is placed in an electric field E bar, and if Q0 is positive, then it will be aligned in the same direction as the electric field. And if Q0 is negative, then it will be aligned in the opposite direction to the electric field. If Q0 is negative, if Q0 is positive, it will align in the same direction of the electric field. Clear? Now, what is dipole? Two equal and opposite charges. Separated by very small distance. And here, if you consider this as the positive charge and this as the negative charge, and electric field is in this direction, and whenever the electric field is applied, then this dipole will get aligned in the direction of the dipole, so direction of the electric field, such that the dipole moment vector will be parallel to the electric field vector. Clear? So it will just here there is a force acting on this direction, and here there is a force acting on this direction, and whenever two equal and opposite forces are acting on the opposite directions, that will give you some torque, and torque will be force into perpendicular distance. Clear? So using this one, we are going to find the amount of torque acting on an electric dipole placed in electric field. Torque on electric dipole placed in electric field. Placed in electric field. Placed in electric field. Consider an electric field So this is the electric field having some magnitude and it is having the direction like this. Now I am placing an electric dipole. I am placing an electric dipole. I am placing an electric dipole Q, so minus Q as Q. So whenever I place the electric dipole in an electric field making an angle theta and the length of the dipole is 2L. Length of the dipole is 2L, and whenever the field is turned on, there exists some force on this one which is equals to QE, and here also there exists some force like this minus QE, such that these two are in opposite directions, so that the electric dipole will get aligned in the direction of the electric field. When such things are going to happen, definitely there will be some torque, because this is same force with this same force. So comparing these two forces are acting in the opposite directions, so that from a common point, then that will constitute some torque in the things that we have taken. So here this is the electric dipole, so this will be P bar, that will be P bar. So force acting on charge Q will be Q E bar, F minus Q will be minus Q. Here minus Q represents that the force is in opposite direction to the electric field, plus represents the force is in the direction of the electric field. Now this is L, right? So this will make some moment, X. So from here to here it will come here. So and this will get aligned here. So this will be L. So here cos theta sin theta equals to X by L, where X equal to L sin theta. X is nothing but the perpendicular distance. So this will be L sin theta, which is equal to perpendicular distance. Here also this will move from here to here. That will move from here to here. So this is also X, which is equals to L sin theta, which is nothing but perpendicular distance. So here we have the force and perpendicular distance equals to L sin theta. So finally the torque acting on the dipole will be force into perpendicular distance. Force is Q E and perpendicular distance is L sin theta, and also this is in parallel direction, it is in clockwise direction, and this will be in anti-clock. Anti-clockwise. So this is also will be QE sin L sin theta. Here I am not considering minus. Why? Because I have already mentioned that anti-clockwise direction. So this will be 2QE L sin theta. 2Q and L will be P E sin theta. Here the big question will come whether it is tau equals to P bar cross E bar or tau equals to E bar cross P bar. So to understand it clearly, we can say that P bar means the electric dipole moment is coming to E bar, is coming to align in the electric field direction, or electric field is going to align in the P bar direction. So what is happening here? The P bar means the dipole moment vector will be coming and aligning in the E bar direction. So the torque on the electric dipole placed in an electric field will be P bar cross E bar. This is not going to happen because it is aligning in the clockwise direction, means P bar is coming and aligning in the P bar. So what is the direction of P bar? So right hand rule, P bar, so if I hold the electric field, it will be inside the board. So torque equals to P bar cross E bar. Clear? Any more doubts in this? Okay. What will happen if a dipole is placed this is minus q and this is plus q. Similarly, this will be like this will be like this. So the total torque will be like this. Clear? So here also P bar cross E bar and PE sin theta. Clear? Now we will just remember torque tau equals to PE sin theta. Now the question is, when T is maximum and when T is tau is minimum, so when it will happen? If the alignment of the electric dipole is in the direction of the electric field, then torque tau will be maximum, means P bar cross P sin 0 0. When it is 90 degrees, then PA cos theta will be PE sin theta will be maximum. So torque tau equals to PE. If they are aligned in parallel, then there will be no direction, means no torque will take place. Tau equals to 0. Here 0 or 180 and here 90 degrees. So when you align the vector perpendicular to the direction of the electric field, when you align the electric dipole in the perpendicular direction to the electric field vector, then the torque will be maximum. If you align it either parallel or anti-parallel to the electric field vector, then the torque will be minimum. Clear? Or so it will be 90 degrees. Here also, if you place it or then the torque will be minimum. Clear this thing? Next, stable and unstable equilibrium. Stable and unstable equilibrium. First, stable equilibrium. If you take an electric field, E bar, and if you place the electric field in the direction of the, if you take the electric dipole and if you place the electric dipole in the direction of the electric field, then there exists no torque on the electric field. Then there is no torque acting on exists on the electric dipole. Here torque will be 0 and net force will be 0. But if you place the electric field, if you take the electric field and if you place the electric dipole in a direction opposite to the direction of the electric field, then here the net torque will be 0 but net force is not 0, and this will call as stable equilibrium. Stable equilibrium, and this is called as unstable equilibrium. Unstable equilibrium means if you just slightly displace this electric dipole with respect to electric field, then it will come to rest by making some maximum torque. But here if you just slightly displace it, again it will come back to the same position as it is. So this is stable and unstable equilibrium. Clear? Now let us solve some problems. Find the angular acceleration. Find the angular acceleration. They have placed an electric dipole. They have placed an electric dipole in the direction of the electric field. This is the initial condition, and they have slightly displaced it through an angle theta. They have slightly displaced it through an angle theta. Then immediately after releasing it will come to rest, right? So in such cases, what is the angular acceleration? It is made. So here whenever you have done something, so it will be P E sin theta. Since is very small, sin theta equals to theta, P E theta, but tau equals to I alpha. We can keep sin theta, nothing will happen. P E sin theta, and alpha equals to P E divided by I sin theta, like this. we can find the angular acceleration of the given question. And if they will ask for time period, if they will ask for time period, means if you take unstable equilibrium, then it will do some oscillations with respect to the mean position. So in that case, time period equals to I equal to alpha equal to omega square theta, here theta will small theta, so theta will cancel, theta omega square equals to PE upon I. So omega equals to 2 pi by t, so 4 pi square by t square equals to PE upon I. So t square equals to 4 pi square I by PE. So t equals to 2 pi root over I upon PE. Like this we can find the time period also. Clear? So that's it for today, and we'll see in the next session. That's it for today.